This conference will now be recorded.
Hi, I am Parangis Bagheri from Neptec, Stockholm, Sweden, and thank you for watching this webcast, Simulation of In-Flight Icing on UAVs. Founded in 2018, Neptec is the official distributor of point-wise grid generation and pre-processing software for CFD simulations. We provide technical support and training for our customers. And besides the software business, Neptec also provides consulting services within CFD. Joining me today is Richard Hahn. Richard is a researcher at Norwegian University of Science and Technology on the topic of icing on unmanned aerial vehicles. He graduated from University of Stuttgart as an aerospace engineer, and after working a couple of years in petroleum industry, he started a PhD on icing of unmanned aircraft. He's a part of the Center for Autonomous Marine Operations and Systems and the Center for Integrated Remote Sensing and Forecasting for Arctic Operations. Richard has more than 8 years of experience with numerical and experimental icing aerodynamics on wind turbines and aircraft. And today he's one of the leading researchers in the emerging research field of icing on unmanned aircraft. He holds a position as lead aerodynamics engineer and shareholder at UBIQ Aerospace, and he's also promoting the application of drone technology in the Arctic with several ongoing projects in the fields of meteorology, glaciology, and atmospheric pollution. Thank you, Richard, for joining. As I said before, my name is Parangis Bagheri, and I am the managing director at Neptec. Before Neptec, I was working at Go Virtual as software manager, and before that, I was working as a CFD engineer at FS Dynamics Sweden. I have my bachelor and master's degrees in mechanical engineering. Okay, thank you again for joining this webcast, Richard. Now I'm going to pass over things to Richard to talk about simulation of in-flight icing on UAVs.
Yes, thank you for this kind of introduction. So, all right, so today I'm going to talk a little bit about simulation of in-flight icing on UAVs. And well, you heard my background. I'm currently a PhD at NTNU, and I've been working on icing related topics in the fields of UAVs and also in wind turbines. And part of the motivation why we do this is because we at NTNU in Norway want to fly drones in the Arctic. So let's talk a little bit about UAVs, or unmanned aerial vehicles, or more commonly known as drones. Drones are a technology which is emerging currently, and we notice that drones and UAVs, they are introduced much more into our everyday lives. And if you look a little bit at the development of drones, then typically the drone market can be segmented into a military and a commercial part. And the projections clearly state that while both markets will grow quite substantially over the next years, it's the commercial market which is going to grow much more. So in other words, this means that we're likely to see that drones for commercial and civil uses will very strongly increase over the next years. And there's several applications for UAVs in civil and commercial fields. For example, already today, a lot of drones are used for agriculture, for construction, for photography and film. And there's a lot of applications which are currently being launched in the fields of marine and offshore operations, but also Arctic operations. And of course, the most prominent commercial applications is drone deliveries, a topic that has been also quite widely covered by the media in the last couple of months and years. So picture the following scenario. It's Christmas and you forgot to order your presents, so you make a last-minute order online and you use one of these new fancy drone delivery services. So you have a drone and the drone picks up your presents and then flies to you, except in this case, the drone would encounter an icing cloud, and this icing cloud would then ice up the aircraft, and the aircraft would then crash and pretty much ruin Christmas for everybody. So this is the basic scenario that we're investigating, and we're trying to understand, and we're trying to develop methods to avoid this. So I'm going to give you a little bit more of the background of the physics of what is happening, and the basic phenomenon that we discuss here is called atmospheric icing. So atmospheric icing occurs in clouds. It's therefore also often called in-cloud icing. And in-cloud icing happens when in a cloud you have supercooled liquid droplets. So these little cloud droplets, they have a temperature below the freezing point, but they're still in a liquid state. So if an aircraft flies through such conditions, then some of the droplets in this cloud will collide with the airframe, and there they will freeze and build an ice shape. So these ice shapes, they can have a lot of different forms. At very low temperatures, all of the incoming droplets, they would freeze upon impact and then create something that we call rime ice, which typically has a fairly streamlined ice form. Whereas if temperatures are closer to a freezing point, not all of the droplets freeze immediately, but they build a liquid water layer on the surface first, which is then gradually freezing, building something that's called glaze ice or also clear ice. And just to give you an idea of how this is looking in reality, this is a video of some wind tunnel experiments that we did. So this is a time lapse over 20 minutes of the different forms of ice growing on a typical UAV airfoil. And you can see the resulting surfaces can be very uneven and are quite likely to have a large effect on the aerodynamics. And the icing effects, the main icing effects from the main effects on the aerodynamics from ice are typically an increase in turbulence and leading to potentially quite large separation areas. And what this usually does is it decreases lift and it very substantially increases the drag. And this is very likely to lead to a situation where an aircraft can crash, for example, due to lowered stall margins or just because drag is too high. And there are different ice morphologies, which are depending very much on the icing conditions. The first ice morphology is so-called surface roughness. This is a rough surface that is building very quickly. I think this picture is taken 2 minutes into icing conditions. And already this surface roughness can alter the aerodynamics of an airfoil or a wing quite substantially, and for example, leading to a trip of the laminar tubular boundary layer and thus increasing drag quite substantially. The second ice morphology is so-called streamwise ice. Streamwise ice occurs in these rime ice conditions that we've seen earlier. It's usually looking quite aerodynamic. So the aerodynamic penalties related to this type of ice are usually lower compared to the other ones. And then we have horn ice. Horn ice is a very complex ice form, which is typically associated with very large penalties because there's large leading edge separations induced by this form. And this is a rather extreme maybe picture from one of our wind tunnel tests on also UAV airfoil. So icing is not actually a new topic. Icing in manned aviation has a long history and has actually been explored since, well, as early as the 1940s, 1950s. And today there's a very wide research basis and a lot of like processes and certification methods and technologies out there that handle icing on manned aircraft. Today, if you fly with a commercial large passenger aircraft, then there's a lot of know-how and a lot of safety measures in there to avoid any complications in icing. However, because UAVs are fairly new technology, there has not been too much research done in this field, and it's very much of a new field that has still a very high implication for UAVs because, as you've seen before, it has a quite high safety concern. Think about, again, drone deliveries, flying in icing conditions, flying, drone deliveries in urban areas. This is a safety issue, which needs to be addressed. And while there's a lot of similarities between manned and unmanned aircraft, there's also a lot of differences. And I want to talk a little bit about some aspects here. So one of the largest differences between manned and unmanned aircraft is that unmanned aircraft come in a much larger variety. There's a lot more different types. So they can come in really like all kinds of like shapes and sizes, which are very much dictated by the application. Typically, unmanned aircraft are tailored for one specific application and thus look very different from each other. So you can have, like a small quadrocopter, for example, which will then have very different icing conditions and icing challenges if you compare it, for example, to a large military aircraft or even an aircraft that's flying at very high speeds. So trying to say here is that because UAVs are much more diverse, the icing challenges are going to be much more diverse as well and need to be very much tailored to the current application. Kind of related to this is that UAVs also come in a very large variety of sizes. Okay, in this graph we can see just a variation of UAV sizes for different groups, and you can see like this: the smallest UAVs can have wingspans of maybe a meter, maybe even less than that, while the biggest ones have wingspans up to 20 meters, which is comparable to smaller commercial passenger aircraft. And this will, of course, affect also how much these aircraft are affected by icing. And there's a physical process behind this, because the smaller an airframe is, the more likely it is to collect droplets. So what you can see in this graph, this is some very simple 2D simulations. And I've chosen here a very specific set of a flight scenario with a fixed velocity, a time span, and temperature, and some icing conditions. And then I've just varied the chord length of an airfoil and to show how the different ice shapes would result. And what you can see here is that the smallest chord length would result in the largest relative ice shape. Note that this is all relative coordinates here. But the largest relative ice shape will also result in the largest impact. So a very large airfoil, here the green line, would have an ice shape which would probably have almost no influence on the aerodynamics, while the very small ice shape would have quite large impact on the ice shape. So what I'm trying to say here, in other words, is the smaller your aircraft, the more sensitive it is to icing conditions. All right. The next point is related to the Reynolds number. Again, due to the differences in size and also the velocities that UAVs fly, UAVs are going to be a little bit different from manned aircraft. So in this graph, you can see the Mach number versus the Reynolds number. And typically, you would find jets and general aviation somewhere in the top right corner. And if you plot in this area UAVs, then UAVs, because they're smaller, typically fly slower as well, would be in an area which is at much lower Reynolds numbers and also at lower Mach numbers. And the main issue arising from this is related to laminar and turbulent flow. So UAVs would typically fly at much lower Reynolds numbers, which means that laminar flow effects would be much more prominent and much more important for them compared to manned aircraft. And when you talk about simulation and also the experiments that have been done to validate these simulations, there's going to be a little bit of a gap, and most of the actual experimental research that we find for manned aviation is performed at Reynolds numbers above approximately 5 million, while a lot of UAVs are actually flying at Reynolds numbers around 1 million or even lower than that. Another difference between manned and unmanned is also the icing environments that these aircraft operate in. Manned aircraft typically operate, especially passenger airplanes, below 30,000 feet, and these are also the icing environments that we know a lot about. As I said, a lot of research has been performed for manned aviation, so we kind of know what kind of icing conditions to expect, and we have icing envelopes that we can use run simulations and to certify the aircraft for this. UAVs, however, are also likely to fly in conditions where we don't have as much experience when it comes to icing. There might be military UAVs that fly at super high altitudes, while there's also a lot of commercial or smaller applications of UAVs that would fly very close to the ground. And this is just icing envelopes, or like icing environments that we don't have too much experience with, and where we also lack, for example, forecasting abilities. And last but not least, the biggest and most important difference between a manned and an unmanned aircraft is obviously that an unmanned aircraft doesn't have a pilot. So it needs to rely much more on autonomous systems. When we talk about UAVs in icing conditions, this has a couple of implications. First of all, ice detection on a manned aircraft is very often done by the pilot itself. There's different instruments that, of course, aid the pilot, but very often the pilot can see ice accretions on the windows or like on parts of the wings himself and make an assessment that now the aircraft is in icing conditions. A UAV typically can't do that and needs to do all of the icing detection fully automated. Because of the altered aerodynamics of an iced wing, the envelope, the flight envelope of where the aircraft can operate is also limited. So in addition to just identifying that there's icing conditions, a change in the flight mechanics of the aircraft needs also to be identified automatically by the autopilot to prevent that the aircraft is going into flight conditions that would lead to a crash. And then finally, if there is icing protection systems on a UAV, which there are several technologies, then a UAV needs again to fully autonomously start these icing protection systems and also turn them off once the aircraft has left icing conditions. And kind of all of these elements have to work in a very automated fashion and kind of work seamlessly with as little pilot influence as possible. And this is again in contrast to manned aviation, where the pilot can take care of a lot of these tasks himself. Okay. I'm talked very briefly about icing protection systems. Icing protection systems exist for manned aircraft in very different versions. We at our university, in combination with Ubik Aerospace, we are also developing and working on icing protection systems specifically for UAVs. Our system is an electrothermal heating system, and it's also a system that, in order to develop it, we are heavily relying on simulation techniques. So this is actually going to be then the next part that I want to talk about is how do we actually simulate icing on UAVs or on any aircraft? And there's typically two different parts to this. The first part is to actually simulate the ice shapes. So this is the goal of this step is basically to simulate what kind of ice would accumulate for a given geometry in some given icing conditions. And once we have the ice shape, then the next step is to simulate the icing effects. So for a given ice shape, how will this affect drag and lift and moment and so on? And these two icing simulation parts, they go hand in hand, but they're a little bit different in the requirements and in the actual processes. So let's start with the first one, the ice shape prediction. And there's a lot of different tools out in the market. There's a lot of the codes that have been developed over the years. Some simpler tools rely on panel methods. Newer methods, of course, rely on CFD methods. And they all work more or less in the same way. So I'm just going to walk you through the basics of how these tools operate. So typically, you start with, for example, 2D clean airfoil geometry. And then you have to put some kind of a numerical mesh around this. So you have to do a meshing. And with this mesh, you would then calculate the flow field around this airfoil. So with this flow solution, you have an idea of the aerodynamic forces and the aerodynamic field around this airfoil, which is going to affect the droplets. So the next thing is that you want to simulate the droplets in the airflow. And there's typically two ways of how this is done. Older codes, they explicitly calculate a few droplet trajectories and then kind of run a statistical method over, say, 100 droplet trajectories to find out how many droplets would hit on the surface of an airfoil and where they would actually hit it. With CFD methods, you can actually calculate the complete flow field, and as a result, you get the collection efficiency. So this is basically, the collection efficiency just means like how many droplets do you hit my airfoil and in which area do you hit it. So you can see here, the highest collection efficiencies are obtained very closely to the leading edge, and everything which is blue on the right side, that's the area where no droplets are actually hitting the airfoil. So based on this knowledge that we know now where are the droplets and how much water do we have in the airfoil, we can then start to calculate the ice shapes. So for this, we have to solve several like energy and mass calculations. There's something called the messenger model that allows us to basically calculate for the amount of given water that we have on the surface, how much ice do we get? And this is then going to be an iterative process. So the icing process is then divided into different steps, into different like discrete time steps, which is then iterated through. So as you can see here, this would be like the ice grab on step 1, step 2, step 3, step 4. So in between each of these steps, actually, this entire circle has to be continued, because after each ice growth step, the airfoil geometry has to be updated, which is now an iced airfoil, which you don't have to mesh again, and then you have to calculate the flow solution on the iced airfoil, the droplet solution, and then the ice growth, and this is then how you iterate through the different icing steps. Now, in the past, the step of meshing the iced airfoils has actually been somewhat the limiting factor when it comes to these icing simulations. And the reason is that to accurately simulate an icing scenario of maybe 20 minutes, you would have easily have to run like maybe 10 steps. So that means that you have to remesh the ice geometry at least 10 times. And then, of course, if you're doing certification of an aircraft, you're not only interested in one certain icing scenario, but it must be like 10s or 20s or even more than that. So the numerical effort here has been quite big. So very quickly, people started to develop new methods of how the meshing can be simplified. And there was a lot of different methods out there, partly relying on automated mesh adaptations so that an existing mesh would, for example, wrap around a newly changed geometry. And these systems work very well for simpler icing scenarios. So this is such an example where the existing base mesh has been now wrapped around the new geometry. But for more complex geometries or ice shapes, these systems usually failed. Today, what has happened is that these tools are usually able to automatically remesh actually the entire geometry and start up with a fresh, automatically generated mesh every single calculation step. This makes basically icing simulations into a one-click story, while in the past there was always a lot of manual work involved. So this was ice shape prediction. And then once we have the ice shapes, then we have to simulate the airflow around these ice shapes. And this is typically a little bit of a separate step. And the reason for this is that the requirements for the mesh and the requirements for the flow solution are going to be much, much higher for this type of simulation. And the reason is because there's a lot of icing effects that affect our aerodynamics, right? So first of all, we have a subscale roughness that is affecting turbulence. We have, increase in turbulence due to leading edge separations. We have potentially unsteady flow features. We have laminar effects, we have laminar separation bubbles that can occur. And to capture all of these, we typically need very high quality measures that we wouldn't obtain from automated systems that I've discussed before. So we at NTNU, what we work with, we do work with pointwise for several years now, and we've seen that we can use pointwise to mesh these complex, like as you can see, very complex geometries in some cases, relatively easily. In our experience, we are very often using the T-Rex measures for this type of case. I think this right here, this is an experimental eye shape. So this is an eye shape that we've collected from a wind tunnel experiment. And the meshing of such a shape with a T-Rex grid is working very well, and it's also working highly automated, which is then really interesting if you're doing studies where you have to investigate a lot of different meteorological conditions. And this is also one of these results. This is a numerical simulation eye shape. And you can see this is a very complex eye shape. It's very complex structures. And with pointwise, we're managing to basically resolve this in a one-step solution. And the resulting flow fields are at least sufficient enough for the type of simulations that we're running at. So just an example, sorry, we're also using this for 3D simulations in a very similar way. In this case here, this is a UAV where we had an artificial eye shape, so that's why it's so smooth, attached to it, and we had some wind tunnel experiments with this that were accompanied with simulations. So just as an example of how we use this in practice, this is a work by one of my students. And what he has done is he wanted to investigate which icing conditions would be the most hazardous for UAV. So what he's done is he looked at such an icing envelope. These icing envelopes are typically used for the certification of aircraft. They basically tell you what different kind of droplet sizes are to be expected with what water contents in which temperatures. And in this envelope, he calculated 16 icing cases. And for each of these icing cases, he simulated the eye shape, and then he simulated the aerodynamic performance penalties related to that. And again, this was done in a highly automated manner, also using pointwise for the performance measures. And this is just one of his results. So this is the color here is related to a lift degradation index, and basically the higher the index, the higher the penalties are. So what we could have seen from this work is that the worst icing conditions are actually icing conditions that are very close to the freezing point. Typically, this would be glaze, or also sometimes called mixed ice shapes that, as I said in the beginning, they build like very complex horn structures, which are then going to have the highest penalties related to them. Okay, to sum this up, icing is a severe hazard for UAVs, and it's limiting their operational envelope. The severity of how bad an icing condition is very much depending on the type of the UAV, on the mission, on its icing environments, and many more parameters. And especially icing may be much more severe for UAVs than for manned aircraft. This is mainly because of their smaller size, which makes them more sensitive to icing. And today we're lucky enough that there are mature icing simulation methods out there, but they do lack validation for UAVs. A lot of the tools and a lot of the methods that have been developed for manned aircraft, but have not been validated too much for UAVs yet. And to kind of combat the risks and the hazards from UAV icing, tailor-made icing protection systems are required that very much reflect on these differences between the manned and the unmanned aircraft, and that are well suited to prevent icing on UAVs. Yeah. Thank you for this.
Thank you, Richard. It was very interesting. Because you had your email address also in your last slide. But if you have any questions regarding the presentation, please contact Richard. And if you have any questions about PointWise or about NEPTEC, you can contact me with this email address. Thank you again for watching this webcast.